Okay, so welcome everybody. So on behalf of the organizers of the colloquy della classe di scienze, I'm happy to introduce Professor Edriss Titi. I mean, actually, Marchiodi will introduce him. So the colloquium will be followed by a coffee break. The coffee break is going to take place exactly in front of us, in the room in Sala del Priore. And we will talk about, we will have a mathematician's point of view on turbulence today. And please, Andrea.
Okay, I'll introduce the speaker. Edriss Titi is a renowned expert in fluid dynamics and, say, nonlinear systems in general, having developed both analytical and computational tools. He has been undergraduate at Technion in Haifa and obtained his PhD in 1986 at the Indiana University Bloomington under the supervision of Cyprian Foyash. He has been Dickinson instructor at Chicago and continued his career at the University of California, Irvine, where he became professor in 1997 until 2014. He also has appointments at the Weizmann Institute in Israel, Texas A&M University, where he is distinguished professor, and since 2018 he is chair professor at the University of Cambridge. He's editor of many journals, such as Physica D, Journal of Mathematical Physics, Nonlinearity, just to mention some, and has been member of several prize committees and advisory boards. He got several recognitions, including the 2020 ICCM Base Paper Award, a fellowship from the Joint Simon Guggenheim Memorial Foundation, an Einstein Visiting Fellowship from the Freie University in Berlin, Gaspar Monge Distinguished Visiting Professor at École Polytechnique, a Senior Simons Professorship from the Polish Academy of Science, a Humboldt Research Award, and a Science Without Boundaries Scholarship from the Brazilian National Research Council. And he will talk about the mathematics of turbulent flows, $1 million problem.
Okay. Thank you, Andrea, for the nice introduction. I already found a typo, but this is normal in mathematics. Did we start the sharing? Is it shared? Oh, wonderful. So it's an exercise to find the typo. Okay. Let me start with a joke, usually about mathematicians. Usually mathematicians says A, they mean B, they write C, and the correct answer is D. So this is why I'm not surprised to have typos. So I'm going to talk today about a topic which is very, let's say, not easy to address, yet I will try to look into it from the perspective of mathematicians, but I cannot really do it without connecting with the rest of sciences. And this is the issue about applied mathematics in general and applied analysis in general. So this lecture is supposed to be not technical at all. I tried to make it as accessible as possible for everybody. So I would like to apologize to the experts. But nonetheless, I hope there is some ideas that basically will shed some light on the subject. And therefore, let me start with the easy, then more difficult, and maybe toward the end, I'll talk to myself. Okay? So let me start with this picture. So what do you make of this picture? Love. Okay. What do you make of this picture? Also love. And now you ask the question, what do you make of this question, of this picture? Fear. Okay. What do you make of this picture? It's also fear. Okay. Now, what do you make of this picture? Turbulence. I mean, of course, you see these pictures, basically this airplane is flying through turbulence, and makes of it is like turbulence. And what do you make of this picture? Oh, well, basically it's a cartoon. Now the pilot tells everybody, now you can relax, the turbulence is behind us. of course, and half the passengers as well, okay? So this is just a cartoon, a joke about the subject. And now, what do you make of this picture? It's a combination of fear, and the lady is in turbulence. That's why she's basically very scared. So turbulence and fear. Okay, this is, as you know, from this picture from Leonardo da Vinci, in which he described some turbulent motions where it's involving all kind of like scales which are involved in this motion, lots of eddies and so on and so forth. In fact, the concept of eddy, my understanding, was introduced by him in this picture. So this is a picture of turbulent flows. So now the question is, what is love? I mean, I know that there are some people here from humanities, they're not only mathematicians or physicists or chemists or biologists. What is fear? And what is turbulence? I mean, I showed you some pictures, and we all recognized from the picture that we're talking about love, about fear, and about turbulence. So you will know it when you see it. So the answer to these things. So you know fear when you see fear, you know love when you see love, you know turbulence when you see turbulence. Of course, that's not really, this is philosophy, this is not really science, so the question is, can we quantify these subjects? I think quantifying love and quantifying fear, trying to find the... So as it says, I mean, finding a rigorous scientific or mathematical framework to understand love, fear, is really far away from being reached. Trying turbulence, maybe, at least we have some kind of like way to measure or quantify these issues, and therefore maybe I will be able to talk more about now turbulence, but not being able to talk about the other subjects. So this is a picture from simulations of turbulent flows. What's characterizing this picture is you can see that it is involving all kind of scales in space, large scales as well as very tiny scales. So it is involving an interacting of different scales. So we observe that there is a wide range of scales involving turbulence. So turbulence is, it's not a definition in a rigorous sense, it's just descriptive. It's a very complex phenomenon since it involves a wide range of dynamically interacting spatial and temporal scales. So many scales in time and in space, they are interacting with each other. This is not really quantifier, but the problem is, or the phenomenon is too complicated because it involves a lot of scales interacting dynamically in space and in time. And now, can we develop a mathematical framework to understand this complex phenomena? That's becoming the question. Now, again, another philosophical statement, regardless of the success on solving this problem, in mathematics in general, the journey of solving a problem and the tools that are developed to solve it often become more interesting than the problem itself. So yes, it's a challenging problem. I try to solve it. I keep trying to solve it. I keep developing tools, etc. Eventually, even if I don't solve the problem, but the tools themselves become useful maybe for other applications. And this is often happened in mathematics. And let me give you some examples. An example is algebra. Algebra was developed to solve a concrete problem. And this concrete problem was socio-economic problem during the days of the Abbasi empire in Baghdad, in which the laws of inheritance in Islam are very complicated. And every time somebody dies, all the scientists, all the scholars have to meet and try to figure out how to divide. Because the father gets 1/3, the daughter gets 1/8, and so on and so forth. And the tools were available at that time simply arithmetics and the geometry of the Greeks, namely Euclidean geometry. And therefore, every time somebody dies, everybody has to drop everything and sit down and try to figure out this puzzle. And that's why the Khalif, in that sense, or the ruler, asked one of the big scholars, says, okay, I would like you to put for me some framework or science solving this issue. And that's how algebra was developed. And this is, as I say, the laws of inheritance in Islam. And Khwarizmi basically put together the laws of algebra. Now, this is an example about a specific problem. So many people think that mathematics usually triggered or motivated by physical problem. Actually, the law of inheritance in Islam is an economic socio problem. Not always has to be with physics, okay? It is scientific in a sense, it's economic in some sense, but not really physics problem. Now, the other thing is I'm going to talk about the Greek problems. There were famous Greek problems. One of them is can you square the circle? Namely, if I give you a circle with certain area, can I write or can I basically design a square with the same area using only simple rules like the ruler and a compass? This is one of the Greek problems. Another Greek problem is why can we trisect an angle by compass and straight line? These are very famous problems, and of course these questions were motivated by the Greeks because their industry at that time was construction, building temples, building beautiful buildings, and the only tools that they needed is basically the ruler and the compass, and therefore they couldn't really do better. So these are the tools, and this was the industrial problem for them. However, to solve some of these Greek problems, in particular, say can we trisect the angle or not, a lot of attempt for thousands of years by the mathematical community trying to address this issue without much success, until basically Galois, Gauss, they developed algebraic tools. This is way after Al-Khwarizmi, not the algebra of Khwarizmi that we know from high school, but it's more abstract algebraic tools about field theory, which eventually they showed that, for example, you cannot trisect an angle, but then these tools that have been developed to address this question, which sounds today silly. I mean, why do I need to find a way to trisect an angle with a ruler and with a compass? I mean, it's really not, but the tools, the mathematical tools that were developed to address it became super important and became very useful in other areas of mathematics. Another mathematical question is Fermat's theorem. The question is the equation x to the n plus y to the n equals z to the n has solutions for every n with x, y, and z are like integers, or like real numbers, or not real numbers, sorry, natural numbers. And you ask, why this is, what is this? This is a silly question. I mean, if you go to somebody who pays taxes and says, I'm investigating this equation, he says, why should I pay tax to support your salary, to basically play with such a game? However, we know that the attempts to solve it, which took many, many, many years, hundreds of years, eventually led to certain area of science in number theory and other words, which is cryptography. Cryptography was developed from all the tools that has been developed in order to solve this kind of question, and now you cannot use your telephone without crypto. We cannot use anything with the satellites without crypto. You cannot use a bank account online without crypto. So the tools were developed to answer questions which are simple of that type, proven beyond doubt that useful. And therefore, this is in some sense propaganda about what mathematics is. Basically, mathematicians prove beyond doubt over the history of humankind that they are asking interesting questions. Even though they sound like on the surface they are, why should I care? It turns out that the tools they develop afterwards is extremely important and useful for application. So now, why do we want to understand turbulence? Okay, we saw the picture. Why we like to understand turbulence? Okay, this is in order to control the onset of turbulence, either to suppress it or trigger it. So you see, I would like to emphasize the word control. Okay? Why control? Because we are human beings are control freaks. We like to control everything. So we would like to control turbulence, namely either to suppress it when it happens, like in the airplane, or to trigger it. Why do I want to generate turbulence? For example, inside the engine, in order to have maximum energy from burning the fuel, it has to mix as efficient as possible with the air so it burns with the combustion very much. And therefore, I need the fuel to be turbulent, mixing with the air in order to basically burn effectively. So I need to trigger turbulence in that sense. So now you can see in the airplane, I would like to suppress it because everyone would like to have everybody calm, and because I would like to have less drag on the wings, so I will have efficiently flying across the ocean with minimum cost. And sometimes I need to trigger it, as I mentioned, in combustion. So we need to understand what triggers it and what suppresses it in order to control turbulence. So this is the main scientific reasons behind that. There are many examples in industry, as I said, and engineering supporting this task. So now, since I need to talk about mathematics, so we spoke about a phenomenon, a description, words. So it happens that this particular phenomenon is governed by system of equations, which are called partial differential equations, called the Navier-Stokes equations. And I'm going to talk about incompressible Navier-Stokes equation, and they are given by this set or system of equations. U is the velocity, which is a vector, which is of three components. So therefore, think about this equation are three equations component-wise. And P is also the unknown, is the pressure. So U is the velocity, P is the pressure, is also unknown. So I have here three components unknown and the pressure, and therefore I have three equations. But divergence of U equal to 0, namely this is a manifestation of incompressibility, therefore give us four equations, four unknown. So it's a fair game, 4 against 4. Now, what is rho? Rho is the density of the fluid, and it is given to me. So the question, what happens with this equation? Can I solve it? It is commonly believed, that this is the equation that model turbulent flows or govern this equation of turbulent flows. Now, I mentioned the word incompressible. Are there other kind of equations? Yes, there are the compressible ones. And now, why I talk about incompressible and when I talk about compressible? It depending on the physical phenomenon I'm trying to capture. For example, if I would like to design commercial airplanes, then we know the speed of commercial airplanes. I use incompressible Navier-Stokes to model the flow around it. But if I talk about aircrafts, military aircrafts, they go very, very fast. They go beyond the speed of sound. Okay, or half speed of sound. Therefore, because the speed is so high, these governed by compressible fluid. And today's talk is not about compressible, because I'm going to talk about phenomena that we observe every day in nature, namely when the velocity involved and the speeds that involved are really reasonable in comparison to the speed of sound. And that's why this is the equation that we'd like to understand. And of course, now we have a set of equations. Somebody would like to understand, are these equations solvable? What means solvable? It means if I give you initial profile for the velocity, can you tell me what happens to the velocity at later time? And therefore, if I know the velocity, I know the momentum, I know the pressure, I know all kind of like aspects of the flow. So, because these are functions of time and space, so for every moment I give you a function, for every moment I have a function, for every moment I have a function. Therefore, the solution is in some sense trajectory depending on time, but in space of functions. And the space of functions is infinite dimensional. And therefore, the solutions of this equation defining an infinite dimensional dynamical system because it takes place in infinite dimensional space. So this is infinite dimensional dynamical system. And now, do we have full understanding of finite dimensional dynamical system? This is the question. Well, the answer is yes and no. So the two-dimensional dynamical systems, the simplest problem is something called the Poincaré-Bendixson theorem. And the Poincaré-Bendixson theorem says the following. If I have an ordinary differential equation in 2 dimensions, and if I have a solution which is bounded, then this solution eventually becoming either periodic or going to a steady state. So the long-term behavior of the dynamic of autonomous two-dimensional equation is well understood. It becomes either periodic or going to a fixed point to a steady state. So two-dimensional dynamical system I understand, but Navier-Stokes is infinite dimensional dynamical system. It's a different problem. So the question is, you know how mathematicians sometimes count. They say 1, 2, infinity. Okay, that's how they're counting. So if you know something for dimension 1, then you do for dimension 2. So probably you can generalize it for dimension which is higher. And the question is what happens there in 3 and higher dimensions. 3 and higher dimensional systems, basically the solutions might become chaotic. So in 2 dimensions, we know it is either periodic or steady state. But in 3 and higher dimensions, it becomes chaotic. So let me now show you a movie. Let me go here and show you a movie. So this is a movie of a pendulum. Do you see the movie? Yes. So it's a pendulum. There are exactly 2 degrees of freedom. The angle that you start from and the kick you give it. So therefore, it is governed by a system of, this is a system of 2-dimensional, the angle and the velocity, or the speed that I give at the beginning. And that's why, when you look to the solutions, it is periodic. Now, what I'm going to have the double pendulum. Double pendulum, it has the angle up and the angle between the 2 and the kicking. So it's basically governed by higher dimensional system of ODE. And you can see, you know, to your eye from experiment that the dynamics is basically crazy. It's unpredictable. It's basically becoming chaotic. And this is an evidence that in higher dimension than 2, the dynamics can be chaotic. So imagine when you are infinite dimensional, like in Navier-Stokes, certainly the dynamics is chaotic. In fact, it is turbulence. And that's why there is an intimate, in some sense, there is an intimate, I close this. There's an intimate connection between chaos theory and turbulence. Turbulence is a prototype of chaos that I would like to understand. And all the theory of chaos was developed with the hope that we can develop some tools to understand turbulence. So the question is, I have finite dimensional ordinary differential equations and have Navier-Stokes, which is infinite dimensional. Now the question, what is the difference between finite dimensional and infinite dimensional ordinary differential equations or evolution equation? Of course, the difference between finite and infinite is infinite. Of course, this is like basically, again, I'm saying a tautology, I'm saying the same thing. But now, can we really characterize it mathematically? Because now I would like to start using some mathematical tools. So ordinary differential equations take place in the finite dimensional space. They r to the power n, while infinite dimensional dynamic evolution equation takes place in infinite dimensional spaces. So, in ordinary differential equation, the unknown is a function of time with value z, and z is taking place in Rn. So the physical space where the solution takes place is finite dimensional, and it is known in advance where it is. However, if I look into an evolution equation, in partial differential equation, for every time I assign a function, as I said, so the values is in infinite dimensional spaces, in the space of functions. Now which space of functions? Is it the continuous functions? Is it the differentiable functions? Is it the 3 times differentiable functions? So in other words, knowing where the solution lives, in which space, is part of the problem. In ordinary differential equation, I tell you in advance where is the solution living. It is in Rn. But in partial differential equations evolution, the space where the solution lives is part of figuring out the problem. Okay? So this is one other difficulty about why dealing with partial differential equations, evolution, and ordinary, it is different. So this is one issue. The second issue is what is the difference between finite dimensional spaces and infinite. So the major difference between finite and infinite dimensional spaces is manifested by 2 important theorems. And these theorems, the first theorem is the Bolzano-Weierstrass, namely if you have a bounded sequence, then it has subsequence converging. But in infinite dimensional spaces, we don't have this property, which is called compactness. And wow, this means I have issues already. Now, why I wanted, if I have a sequence bounded, has subsequence converging, because usually to solve a problem which is infinite dimensional, I really approximated by finite dimensional problem. And then I try to solve the finite dimensional problem approximately, and then I make my resolution finer and finer. Therefore, I get a sequence of approximate solution. Hopefully, I can find that this sequence converging, and maybe at the limit, I reach or I catch a big fish, namely the solution of my equation. So that's why we need theorems, which tells you if you have sequences which are bounded, has subsequences converges, or what's so-called compactness theorem. The other issue is the norms are not equivalent. Namely, in finite dimensional spaces, the norms is equivalent. Namely, if you show that one norm of the solution is finite, then all of them are finite in finite dimensional spaces. In infinite dimensional spaces, that's not correct. I can show that one norm remains nice, but some other norm could become infinite. And this is additional difficulty. So if you say, oh, I can show you that the solution in this norm remains finite. Good, congratulations. But what about other norms? So that's why this is additional problem from the mathematical, technical point of view, difference between evolution equations, namely between ordinary differential equations and partial differential equations. Now, I'm going to talk a little bit about technical stuff here. I'm going to introduce something called Sobolev spaces, which are the space of functions that when I talk about Fourier expansions, this is e to the power ikx, like sines and cosines, and these are the Fourier coefficients. I wanted functions which are the Fourier coefficient decaying fast enough to kill this algebraic growth. When S is positive, this is growing algebraically, but if the phi k is decaying fast enough, the product, the sum of the product is decaying. Therefore, the larger the S, I need phi k to decay to 0 faster and faster for the series to converge, which means phi k is smaller and smaller for S larger, which means I give less and less weight for high frequencies. A rough function means very oscillatory. A smooth function, it's oscillate, but not really very much. Therefore, it doesn't have fast oscillations. And therefore, if the weight for the fast oscillation is small, means the function is smooth. And that's why we would like to see that solutions live in this space, but for large S, namely that the solution is nicer and nicer and nicer. Now, why Sobolev spaces of all the kind of spaces? Why not classical spaces? Because these spaces, in particular these Sobolev spaces, happen to be Hilbert spaces. And then I can use some of the geometry of Euclidean that I can extend in Hilbert spaces, like Pythagoras theorem, inner products, and stuff like that. But it's an infinite dimensional version. These are more user-friendly from the mathematical analysis point of view. So I come back to the Navier-Stokes equation, and now, of course, Navier-Stokes equation, usually fluid is confined in some domain or exterior domain. But mathematically, in order to understand the subtleties, let me disconnect any effect of the boundaries at the moment, and then I look to the equation evolving in periodic boundary condition, and I would like to see if you give me initial data, which is nice, does the solution remains nice? Does the solution in interesting norms, in relevant norms, remain under control? And this is a work that was done long time ago by Jean Leray in the 32 and 34, way before any of us was born, okay? Which basically Leray proved the following interesting theorem, that for any time you give me, there exists something called weak solution of the Navier-Stokes equation, which basically this solution is continuous in time with values in the Hilbert space L2. But in the weak topology, this is a technical aspect, but it is continuous in time with values in the space L2. Why I need it to be continuous in time? Because I wanted to know when t is converging to 0, I recover the initial value. So I want things to be continuous in time. And also the H1 norm, namely the Sobolev norm H1 norm, namely the gradient are square integrable. Why I want the gradient to be square integrable? Because this is a manifestation of the dissipation due to the viscosity. So I need solutions to be there. Now, this is a beautiful piece of work which shows global in time for any initial value, we have solutions of the Navier-Stokes equation. Now, what's the shortcoming of these solutions? We cannot prove that they are unique. Namely, I start with this initial value, I get a solution. If I repeat tomorrow the same experiment with the same initial value, I might get a different solution. Non-uniqueness. So this is one of the shortcomings of the one established. So it's an open question whether these solutions are unique or not until now. Nobody knows how to settle this thing. In fact, the lack of uniqueness, to some experts' point of view, may be related to the phenomenon of turbulence, that I cannot predict which direction the solution is going to take place starting from some initial data. And that's why actually Leray called these solutions turbulent solutions. He called this week's solution turbulent solution, because maybe the lack of uniqueness is intimately related. Maybe it's speculations. Now, what about strong solution? What if I demand the solution is nicer initially? Then he proved again, Leray, that the solution continues in time, but with values in the space H1, not in L2 and H1. Wow, this is much more regular, much more demanding from the solution. And the solution is also satisfying this property, namely it is living in this space, okay? Now, this is strong solution. The problem is that Leray could not show that for all time, strong solution exists. Weak solution, he could for all time. But strong solution, he couldn't show it for all time. And what he could show, basically only for short time, you have existence and also uniqueness of strong solutions. And I will come into this point in a minute. And now, because there are physicists in the audience or listening to us, now what happens? Let me give you a different formulation of the Navier-Stokes equation. Namely, try to get rid of the pressure. So if I take curl of the equation, this is U, omega. Omega is the curl of U, namely the vorticity. Then the vorticity is obeying this evolution equation. It is diffused because of the viscosity. Nu is given positive constant, the viscosity. It's transported, but then there is this term which is called vorticity stretching. This term in 2 dimensions, identically zero. In other words, in 2 dimensions, I don't have stretching. In other words, the direction of the vorticity is not changing. Only the magnitude could go up and down, but it cannot because this is zero. So it is transported by this term and diffused by this term. And therefore, the vorticity under control in 2D, and that's what allows Leray, this is a different way, a backdoor justification, while Leray could show that in 2 dimensions you have a global existence and uniqueness because the vorticity in 2 dimensions is under control. But in 3 dimensions, I have this term which is non-trivial, stretching, because omega is like derivative of U, it's curl of U, and I have a gradient of U, so this is morally speaking like omega square, and therefore the evolution of omega like omega square, it is like an avalanche. The rate of change of omega, depending on omega, the larger, or the snowball, the larger the radius, the more it collects. And therefore, the next round becoming larger and larger and larger, which is that might lead into kind of like a blow up or singularity. So in 3 dimensions, this is non-trivial, and therefore the equation like omega dz dt equals x squared, morally speaking, which is potentially could lead to a blow up. So now we understand that why in 3 dimensions Leray could not show a global existence, because he needs to control the vorticity. And to control the vorticity, he needs to control this term, and he couldn't do that. And that's why he can show only short-time existence and uniqueness. Not more, not less. So weak solution exists globally, but they are not regular enough. They are rough, and I will talk about that hopefully later, about the roughness issue, because it's related to turbulence again. And as I told you, the lack of regularity and lack of uniqueness basically made Leray and other experts to believe that there is some kind of like this is related or can really represent turbulence in a more honest way. While strong solution, they are nice, but for short time. And what happens after that short time? Because these strong solutions, which are exist and unique, actually they can continue their life as weak solutions. But then weak solutions need not to be unique. So when at this time the strong solutions stop to exist, maybe they transfer phase or transfer shape to becoming weak solutions, but infinitely many. And this is basically somehow why mathematics trying to understand turbulence by understanding what happens to individual solution. Do they become singular in finite time? And what's the form of the singularity? So maybe we could understand what's happening with singular behavior, and in particular with vorticity, namely swirling inside the fluid or small eddies in the fluid, as in the picture or by Leonardo da Vinci. So I go back to the Navier-Stokes equation. So in three-dimensional case, we have global existence of weak solutions, short-time existence of strong solutions. This is an old result of Leray. And now you ask, what happens from 1932 until today? What did we do? We have been earning salary. Well, we try to understand better. It's like basically when somebody writes, like the prophets say something, then it takes hundreds and hundreds or thousands of years for the priests to keep interpreting it, okay? So we try, in some sense, try to understand in somehow these results and maybe simplifying things and looking to some kind of like different context, maybe we can understand better what is happening. So uniqueness of strong solutions, it is really established. Now the open problems, there are two major open problems. The first one is uniqueness of weak solutions we don't know until now. And another question, which is the global existence of strong solution, namely, do strong solutions stop to be nice after finite time, or do they exist globally in time? And the second question is the millennium problem. Do solutions of Navier-Stokes remain finite and nice all the time about strong solution? And this is the millennium problem. Now people can ask, why did the mathematicians choose Navier-Stokes and not really some other problems in PDEs which is more complicated, like Einstein equations, which are more involved? Why Navier-Stokes? Well, this is, again, it's a philosophical question. Mathematicians are really are attracted to problems that are easy to formulate, but they are challenging. So Navier-Stokes is easy to formulate. Why? Because it's a nonlinear equation, but the nonlinearity is u dot nabla u. It's after all quadratic in u. This is the simplest nonlinearity you can think about. You cannot think about simpler nonlinearity than quadratic, and yet we don't know how to do it. So it is an attracting, in the sense of, like we say, in addition to the applications, but it's easy to formulate the same way with why Fermat's last theorem was attracting, because it was easy to formulate. You can explain to kids in high school and basically ask them, can you do something about this? So now, people start, as I said, you ask question, what did we do afterwards? Then people start really trying to find conditions about what could go wrong. Yes, the vorticity could become infinite, but is there other quantities that if I can control, they are okay? So there is this criterion, which is if you look for the L6 norm in space, and you take it to the power 4, integral in time, finite, then the solution remains nice up to time t. I would like to emphasize this particular results because of Prodi. Okay, because this is one of the conditions were introduced by Prodi, who was professor here. Okay, he was one of the pioneers and the leaders in the mathematical theory of Navier-Stokes equation, and this is one of the criteria. He has a whole family of criteria in order to show existence or global regularity, and this is one of them. His name will come again later, the name of Prodi. So in some sense, is this quantity remains finite or not? This is the $1 million question. Does this remain finite or not? If it remains finite, then we have global existence. If it's not, then we don't have global existence. So this is the millennium problem, or this is what's so-called figuratively, literally, it is the $1 million questions. Now, jokingly, okay, I would like to call this the minus 12 bulls or cows problem. Why? Why minus? Because rumors, legend said it, maybe it's not correct, that when Pythagoras was blessed with his theorem, he sacrificed 12 bulls to the gods, thanking them for proving this big theorem. Nowadays, we get money if we can prove a big theorem, but in his case, or that again, he sacrificed 12. So that's why I would like to call it the minus 12 bulls or cows, just jokingly about the difference in the culture, etc. The question is, yes, suppose there is a singular point. There is singularity. Can't you find it numerically or experimentally? Is there an evidence? There is a work by these distinguished mathematicians, Caffarelli, Cohen, and Nirenberg, in which they said the following. Suppose there is singularity. Now, if you look to the space, because that's where the solution lives, and time as another dimension, so you are in 4 dimensions, space and time, and you look for a singularity at time and where in space. So you look for this set in space and time. They proved that if there is singularity, the Hausdorff dimension of this singular set less than 1. In some sense, it is less than a curve in 4-dimensional spaces. So it is very meager. It's almost not possible to see it. Now you see it, now you don't. Now you see it, now you don't. And this shows you why it is really extremely challenging to prove or to show to find the singularity. Of course, there are many results, generalization of Leray and so on and so forth. I'm not going to talk about them today because otherwise I will bore you a little bit, and basically I don't want to lose the other people in the audience. So there are some special results about global existence and uniqueness and some extra assumptions. For example, there is a result by Fujita and Kato in which they prove if the initial data is small, you have a global existence. Then there is a result by Ladezhanskaya. If you look for flow inside the domain, which is a revolution domain around the axis. So this is the cross-section of the intersection of the domain. This quantity here is the cross-section here of the domain. This is the cross-section. Okay? So it says that if the solution axis symmetric, one can show global existence and uniqueness of strong solution. But this is restricted, kind of like geometry, not a full spiel, not the full Bledge Navier-Stokes in 3 dimensions, because there is some symmetry. Similar results have been proven by Leibovitz, Mahalov, and myself for helical flows. Again, so there are some particular results which are of some interest in this situation. Okay, now I would like to look into the remark. So in the axis symmetric and helical flows, the stretching term is non-trivial. So they are really interesting because the vorticity stretching term is the challenge in 3-dimensional Navier-Stokes. So we can see some solutions of 3-dimensional Navier-Stokes with a huge vorticity stretching, huge bad guy, but still we can control everything and we have global existence. Unfortunately, if there is no viscosity, when we talk about Euler equation, we don't have this property. We're still unknown if you have inviscid flow, namely Euler equation, when the viscosity equal to 0, if you have global existence of solutions under this symmetry. Okay, as I said, there are many other results, but I don't want to talk about them now. I would like to move on. So, would like to talk about stability of strong solutions. Of course, one can show that if you have a strong solution for some initial data, there is a whole small vicinity of initial data where you have a global existence. So namely, if you catch a good solution, in fact, you catch infinitely many around it. Okay, this is a result which is by Ponce, Sideris, Recche, and myself. Now, what happens in Euler equation? There is an old result of Lichtenstein, in which he proved, like what Leray said. Leray proved it for Navier-Stokes in 1934, after Lichtenstein. Lichtenstein did it in 1925 for Euler equation, but then he proved short time existence and uniqueness for Euler equation, but short time. And then what happens, Eben and Marsden and other people proved the same result, but for initial data in the Sobolev space HS, for S is bigger than 5. over 2. So what happens is that for the Euler equation, we have only short-time existence and uniqueness. And does there exist a global solution for 3D Euler equation? This has been an open question basically until 2011, when Emil Widman in his PhD thesis, based on the work of Camillo Delellis and Laszlo Szekahidi, Szekahidi was his advisor, basically showed the existence of weak solution. So from 1925 until 2010, we couldn't establish weak solutions. Where Leray, in one work, he showed existence of weak solution globally and short-time existence of strong solutions. While for Euler, people proved that only for short-time existence of strong solutions, and later it took like almost 100 years or something to prove that. And that's what I said. Sometimes the problem is so challenging, it takes decades upon decades to establish it. To show that exist weak solutions, it took almost 9 decades to do it. So anyway, so I don't want to talk too much about these things because, as I said, I would like to move into other aspects because I don't want to lose completely everybody. So in this audience. So I would like to talk about other aspects, which is to connect with other areas of science. So far, I spoke mathematics and analysis, okay? And I can keep talking about that. I give like a whole mini course about it, but we wouldn't shed much light about these challenges. But I wanted to answer the question: what happens since 1932 until now? I mean, there were many small results here and there, trying to understand the big monster, but still the big monster still there, and we couldn't conquer the big monster. Now, I'm going to talk about anomalous dissipation. And now I would like to connect with physics again and with engineering. So what happens is that Navier-Stokes has viscosity, and viscosity is responsible for dissipation of energy. What happens when people do experimental measurements and let the viscosity becoming smaller and smaller and smaller, they realize that instead that the dissipation mechanism go to zero, it remains bounded from below. And people call this dissipation anomaly because why? Anomaly because it should be zero, but it is not really zero. So there is anomaly here. And this is experiments. Now, can we figure it out? Can we develop mathematical framework to understand what happens here? So, as I said, this is the equation of evolution for the energy in Navier-Stokes equation. That's what's responsible for dissipation of energy. When viscosity is smaller and smaller, it turns that this does not go to zero. It remains somehow positive that eventually there is dissipation of energy. That's what energy dissipation. Can we prove it? This is the question. Now, there's a guy who's a chemist or physicist, whatever, called Ansager. Ansager basically thought about this anomalous dissipation, and his thoughts were, it is of some interest to note that, in principle, turbulent dissipation, as described, could take place just as readily without the final assistance of viscosity. That's what dissipation anomaly. That's what it is based on experiments. That's what he found. In the absence of viscosity, the standard proof of conservation of energy does not apply. Namely, Euler equation, in the absence of viscosity, does not really have conservation because the velocity field does not remain differentiable. In other words, the solution is rough, and that's why, because the solution is rough in turbulent flows, you have dissipation anomaly. So when people do experiments and see there is dissipation anomaly, it's a manifestation that there is maybe singularity in the flow, and that's what mathematicians trying to prove. Okay, however, he showed that basically, yes, it's not differentiable, but if it is a little bit regular, namely Lipschitz Holder continuous of order 1/3, then one can show that the energy is conserved, and this is a result that has been proven for the Euler equation. If you are smooth enough, if you're not smooth enough, then you don't have these things. And now, I gave you the scenario of mathematics. I told you that the physicists observe something, then we try to help them to prove it. or disprove it, okay? Or say these kind of like prophets, like Onsager, is he right or not right, and trying to prove it. And there's some big program going in this direction, and until now we don't know how to prove dissipation anomaly. And now the question that somebody could say, okay, with all these powerful computers, can we compute turbulence? Well, it's a really interesting question. Now, there is some quantity called the Reynolds number, which tells me the ratio between the intensity of the nonlinear terms, which are the troublemaking, versus the viscous term, which are the dissipation and the smoothing effect and so on and so forth. So Reynolds number, in some sense, measuring the trouble versus the bad guy versus the good guy. How many bad guys versus how many good guys? And if the ratio is very small, means you have better good guys, and therefore everything is smooth and nice. And that's why what we're interested in turbulent flows is for high Reynolds number, because that's where action is taking place. So now, if you'd like to talk about weather prediction, okay, then one discovered that the Reynolds number in the weather is something like 7 times 10 to the power 8. It's a lot. And now if you'd like to use the computer, namely to discretize the Navier-Stokes numerical analysis and trying to solve it, you have to discretize the time and space. People did some calculations following some theory of Kolmogorov and realized that usually the number of equation that you need is usually a Reynolds number to the power 9/4. And as a result, if I would like to predict the weather precisely, I need to solve at every time step 10 to the power 18 equations, namely the values at the points. These are linear algebra. Namely, I have unknown vector of length 10 to the power 18 multiplied by a matrix 10 to the power 18 by 10 to the power 18. I need to invert the matrix, excuse me. We have difficulties inverting matrix 3 by 3. Imagine 10 to the 18 by 10 to the 18. This tells you why the problem is so complex. In order to solve numerically, at every time step, I need to invert matrices of the size 10 to the 18 times 10 to the 18. This is for weather prediction. You see, suppose I would like to have a short video, numerically exactly, for flow around the car. So when I talk about flow around the car, in this case, the Reynolds number is like 10 to the power 5. And in order to solve this, the number of equations I need to solve is 10 to the power 10. Oh, this is smaller, it's 10 to the power 10 matrix times 10 to the power 10, I need to invert. Still huge, and I cannot do it. And now you ask yourself, okay, this is the number of equations. Thank you very much. You told me how difficult is the problem. Now, practically, suppose I give you the best computer in the world, the one which is underground that nobody knows about, okay? And you ask the following question. How long does it take to compute flow around the car for a short time, like for a few, like 1 minute? I would like to make a video. How long does it take to the biggest computer in the world, the supercomputers of the world, for this flow around the car, which is 10 to the power 10, 10 to the power 10. And then let's start with a guess. Does it take 4 years? How about 40 years? How about 400 years? How about 4,000 years? So, goodbye, computer. In order to have like a short video about flow around the car, I need to wait 4,000 years for the biggest computer to tell me. I might watch it and go home. So this shows you how challenging is the problem from the computational aspect point of view. So mathematics, we're trying to prove existence, uniqueness, and then physicists trying to observe something in the laboratory, we're trying to explain it mathematically, then numerical analysts try to do it, but then it is too big of a bite. I cannot do it. It's a huge, as somebody described turbulence, huge elephant. Somebody is trying to catch the ear, the other person trying to catch the nose, but nobody is daring to get close to the legs because they will be smashed. So that's what different approaches to turbulence. Now, you do experiments. So you have a tunnel, a wind tunnel. You put a probe at some point, measuring the velocity at that point. One component of the velocity at one point and different times. And therefore, when you basically measure the velocity at times, say between 0 to 5,000, you get this picture, the first picture. And you see that this is very going up and down. It's very erratic. It is turbulent. So the velocity at that point in time is like erratic, it's going like crazy. And now, you say you go for lunch, and you come up after lunch, and then you look to the measurements. So now, not from 5,000, from 19,000 up to 24,000, okay? You get this picture. You see that this picture and this picture, both of them are erratic, but you can see you don't see that there is relation between them. I mean, this is erratic. You cannot read this. This could be like the stocks market. It could be anything. And now what people do is, you know what? This is individual trajectory in time. Let me do the histogram. And then you do the histogram of the first, and you do the histogram of the second, and what do you get? Hallelujah. Wow. It's the same histogram, which means the individual solutions are going crazy, but the statistics is the same. Wow, this means maybe I should give up about individual solutions and talk about statistics. So, now I need to talk to Franco. Okay? Can you please use your measure theory and whatever, can you help me to try to identify the statistics, namely what are the invariant measures involving this. So basically what I'm seeing here, if you take, this is the flow which is erratic going up and down, I look for the average flow, this is green line, I hope you see the green line, which is the long average, and then I have the fluctuation and the mean I call it phi bar, and the fluctuation phi prime, and therefore if I take Navier-Stokes, I take the velocity v, I decompose it into v bar, namely the average plus fluctuation, the pressure P bar plus the fluctuation. And then I go, this is the Navier-Stokes equation, it's given to me here. I go and I write the equation for V bar, the average. Why I want the V bar? Because as I showed to you here, okay, the solution is fluctuating like crazy, but the average is beautiful, the green line. So maybe I can capture it, maybe I can compute it because it's smoother, it is nice. So therefore I need to find equation for V bar. The nonlinearity is quadratic, V bar is average, and therefore I need to look for the average of product. We teach kids that the integral of product is not the product of the integrals. Okay, and therefore, what happens that V bar, when I look to this, I get V bar dot nabla V bar plus fluctuating interaction with fluctuation average. But I want to solve equation for the average. But in order to find the solution for the average, I need to find V bar. So I'm chasing my tail. To find the average, I need to do fluctuations. Then he says, let me write an equation for the fluctuation. Then you find that you need equations for the third moment, and so on and so forth. And you find that basically you're chasing your tail. In other words, there is no closed equation for the average, which is the nice one, which is represented by the histogram, the probability distribution. I cannot find an equation for it. And that's why what the biggest brain of turbulence modeling engineering doing is how to model this quantity, the V prime dot nabla V prime, this quantity here, the trying as much as possible to model it in terms of V bar, and this is what's called the closure problem in turbulence, and that's what engineers do. Engineers based on experiment trying to really replace V bar dot nabla V bar average in terms of V bar, and this is modeling. This is hand waving. There's no science behind it other than, that's what we call it sometimes plumbing. Okay? You do it, you test it, well, it works, thank you very much. And now I'm glad to tell a joke about John Lumley, who was one of the biggest brains in turbulence modeling. He was an engineer at Cornell University. One time I attended the lecture. He was plenary talk in the American Physics Society. And then he started his talk saying, well, every time I take an airplane, I look at it and says, my God, what model did they use to model it? What closure model they used to model it? I hope none of mine, because I'm taking it, because he knows the shortcoming of his models. So this is a joke, but this is a real thing. I heard him saying this stuff. Okay, so now Therefore, we need to talk about statistical solutions, namely probability distributions or measure invariant probability measures in the space of solutions. Do we have such solution? And again, the name basically, are there probability invariant measures associated with the solutions of the Navier-Stokes equation? And these are called statistical solutions. Do they exist? At least in 2D, yes. It's a result from 1975 by Foesch and Prodi. Again, our Prodi here, basically was one of the pioneers, not in the statistic, not only studying individual solutions and do we have singularity or not, but he was one of the pioneers in trying to understand statistics, realize the importance of statistics, and therefore now, do they exist? In fact, they do exist, and there are infinitely many of them. Because there are infinitely many of them, again, we are chasing our tail. Which one is the physical and which one is not physical? And now it's becoming a problem of identifying, choosing, selection mechanism, which one of these probability distributions is the physical one. And still, the verdict out there, we don't know which one, and so on and so forth. Now, so what would be the physical relevant ones? We don't know. So you can see now, I was willing to give up on details, to talk about averages. Again, I cannot solve it. Whatever I'm attacking this elephant is basically hitting me by the nose and basically kick me away. It is basically unconquered from mathematics, from computations, from engineering, and so on and so forth. Now, final couple of slides is, okay, I cannot do the Navier-Stokes and turbulence for airplanes. Well, can we say something about climate? Okay, so there are large oceanic and atmospheric basically circulation currents. These are big currents in the ocean, but they are at the continental scales. Very, very, remember, I was talking about turbulence all the time. I said it is a matter of scales, because there are small scales, larger scales. Suppose I would like to give up on fine details, look at continental scales, okay, planetary scales. So can I capture something like that? Now, okay, the atmosphere or the ocean is very, very wide, but is very thin. It could be tens of thousands of kilometers, but few kilometers depth. And therefore, the aspect ratio is very small. It is very thin. In fact, if you look to the atmosphere on the Earth, the ratio of the thickness of the atmosphere to the diameter of Earth, it's almost like the skin of the apple on the apple. So it's almost like flat, like two-dimensional. In any case, there's mathematical theory by geophysicists and as well as mathematicians, in which basically to capture these larger scales, they look into models capturing the larger scales phenomena. And of course, these are asymptotic models. And then we can prove something rigorously about the derivation of such models. So it's all about matter of scales. And basically for the Rayleigh-Bénard convection, because in the atmosphere you have a fluid, but you have temperature. The temperature is basically moving the fluid here. But then, because the fluid is moving, it's carrying temperature along, and they are coupled, and this is called the Bose-Einstein approximation or the Rayleigh-Bénard equation. This is the equation of interest, of incompressible, and these equations are similarly difficult to understand as Navier-Stokes equation. But when you try to solve this equation in the context of the climate, namely in the context of planetary scales, one gets some other set of equations. So geophysical models, are geophysical models better behaving because taking advantage of the thinness of the atmosphere or the thinness of the ocean in comparison to its width? Because I'm talking about large width. So climate and weather. So what's the difference between climate and weather, as Lawrence said? Well, climate is what you expect and weather is what you get. You go on vacation, to Spain, you expect the weather to be nice all the time. But what happens to be raining that day? It's your luck, okay? So there's expectation, namely the average. And that's why if we would like to talk about climate, we need to talk about larger scales. And the question, do these models behave better? It tends to be yes. And this is some of the work that we did. So we proved that for the primitive equation of oceanic and atmospheric dynamics, you have global existence. You don't have the issues that you have in 3D Navier-Stokes equation. And then the next thing you talk about, All right, now I know that atmospheric dynamics is nice, but not for the weather, for the climate, namely for planetary scales. Now, I would like to couple it to moisture for cloud dynamics. Why? It seems to be that the clouds in Indonesia, close down there, there's a long cluster of clouds affecting the weather in Europe. And that's why we need to understand the clouds formation and so on and so forth. It seems, again, the mathematics of understanding cloud formation coupled with atmospheric dynamics at planetary scale, we understand that this is, again, result of Jean-Kai Lee, Rupert Klein, and Sabina Hittmeyer with myself, in which we basically have some knowledge. And I would like to thank you very much for the invitation. I would like to thank you for your attention.
Thanks, Edriss, for the wonderful talk. Is there any question? Okay.
Hi, thank you very much for the talk. From a physicist perspective, the Navier-Stokes equations comes from, truncating higher order nonlinearities. Is there some understanding of the role that these higher order nonlinearities could play in changing the behavior of the solutions?
Well, this is an interesting question. I think the answer to that question is like, if tomorrow somebody shows that Navier-Stokes mathematically are not good, then all the physicists will jump and say, we told you, here is the right model. So I would like to get the right model that commonly believed by physicists so I can work on it. Now, the question, what do you mean common? What do you mean the right model? So far, some of the simulations using Navier-Stokes as is, comparison with experimental data and statistics, is doing a good job. And that's why people are kind of like commonly believe maybe it is the right model. But you are right, maybe it is not really the right model, and one has to take other considerations or other effects into consideration. But at the moment, that's the model that was provided to us by you, the physicists, and by engineers, and we work with it. And airplanes are flying, even though designed using the Navier-Stokes equation. That's so, to large extent, the answer is, that's what we have. But I don't rule out that maybe the model is not good, because I didn't derive the model from other principles than the continuum mechanics, except that there is another community, the kinetic theory community. Kinetic theory community, they talk about Boltzmann equation, etc., and they have some small parameters, and some results have been shown that if this small parameter goes to 0, you converge to Euler and Navier-Stokes equation. Again, maybe what they did in the Boltzmann equation, the expansion, maybe they also put some kind of approximation that assume that it is behaving like this and this. So in that sense, this is another evidence that maybe these are the right model. But now, basically, it says, how do I know that the Boltzmann equation are correct? So, okay, it is becoming like who is first, the hen or the egg?
Thank you.
You mentioned this result about infinitely many statistical distributions, right? Can we find a handful, like explicitly? Is it possible to compute? And maybe a follow-up related to that, if we put some additional inputs that we would like it to be, I don't know, like a scale invariant or something like that, does it bias anything? Or?
Okay. So you asked a very interesting question. And of course, you know, I would like to be kind of like street smart and answer the question. Every steady state of Navier-Stokes, the delta function there is a probability invariant measure, because I start there, I'm there. In fact, it's ergodic even. If I have another steady state, I take the delta there measure, it is invariant measure, and it's probability measure because all the word is 0, and this particular point is measure 1. Now, if you have a probability measure, another probability measure which is invariant, then any convex combination between them is also probability measure. And it's invariant because this is invariant, the union is invariant. How many I can have? All the convex integration. I rest my case. I have infinitely many already. Now, this is trivial, and now that's why we need, in some sense, to have additional criteria for selecting to rule out these trivial examples, namely the really current question that we don't know how to show. Because Navier-Stokes, in 2 dimensions at least, it has an attractor. The attractor is compact, it has finite dimension. Can we construct an invariant measure, probability invariant measure, which is supported on the attractor, namely that the attractor, if you take any point in the attractor, you take a ball, the measure of this intersection remains positive. Do we have such a measure? We don't know. It's an open question. So if we establish something like that, then maybe this is like, in some sense, this is kind of like first step that we are in the right direction, that could be physical. But maybe also like these ones, maybe infinitely many, I don't know. You know, invariant measures on attractors, even for simple chaotic dynamical systems of maps of the interval, like the Henon map, etc. There is something called the RSP measures, namely the Ruel, Sinai, Bowen measures. Constructing these is a nightmare. And you have it only for very simple examples of canonical systems of maps. Even for Lorentz system, which is 3-dimensional, which has been beaten to death, finding a probability invariant measures supported completely in the attractor, it's still not established. So that's why many people are trying to attack, even though Lorentz does not have much to do on Navier-Stokes, but if I establish it for Lorentz, maybe there is hope for Navier-Stokes.
Okay, I have one. So you mentioned this result when you have when you're nearby a global solution, you're also global.
Yes.
Is it a kind of orbital stability result?
Is what? Sorry, it? What?
Orbital stability?
Well, it is, maybe, yes. It is a shadowing in some sense, yes. Now, such a result is known for Navier-Stokes. It is unknown for Euler. Mm-hmm. So there is a viscosity effect, namely the stability, or if you take Hamiltonian systems, you don't have such a thing. Why? Because Hamiltonians, you cannot be attracting. If you attract in some direction, you are not attracting in the other direction. Therefore, you might basically, for a while, remain, but then if you catch the unstable direction, you go away from it, and then maybe you don't have, you don't really trace. But it is an orbital, or if you want, or a shadowing lemma, namely. So if you take a point where you have exactly global solution, the whole neighborhood will basically be tracked and following this particular solution, thanks to the viscosity. Mm-hmm.
Yeah, thanks for the talk. I have a small comment. So you mentioned why, people could ask why we don't care about the Einstein equations, but Navier-Stokes equation. But actually, there's something called the fluid gravity correspondence. I have a vague impression that in some d+1 dimensional Einstein equation in certain limit could reduce to a d-dimensional Navier-Stokes equation. Something like it should be relativistic fluid, like perfect fluid will correspond to the Schwarzschild solution in Einstein equation, something like that. So yeah. It is in some sense solving the Einstein equation. Well,
okay. Thank you for this. Well, that's fine. I probably I don't doubt what you're saying, and I see it. Indeed, we see. I receive many papers to handle as editor about like relativistic fluid dynamics and so on and so forth. What I said, I didn't say, and this is to be clear, I didn't say that Einstein equations are not important. No. What I said is that mathematicians are biased in their taste. In some sense, they would like to choose problems which are easy to formulate, but challenging to solve. This is like we are like kids, okay, who enjoy toys which are really simple to figure out at the very beginning, but then there's a challenge. That's how we, and therefore, simplicity and elegance, that's what drives the community, and it's a taste. It's a matter of taste. Now, the other equation, the Einstein equation, etc., are more challenging, are more difficult, but here is a simpler problem which is challenging enough, and we don't know how to do it. So let's start there. So this is a matter of taste, not more and not less. And I wasn't in the mind or the brain of the Clay Prize committee, but I can, in some sense, speculate of why they chose this particular problem.
All right, so I guess we can ask further questions at the coffee break, which is right across the room. And so we can thank Edriss again for the great talk.
Yeah. I would like to thank you again for the invitation and for your attention and for coming here. It's a really great honor and pleasure to speak in the School of Prodi. It's really a big pleasure and honor. Thank you.